Welcome back to the deep dive. Our mission here is, well, it's to take these huge stacks of technical stuff, sources, and turn them into practical knowledge, something you can actually use.
That's the goal.
And today we're doing a foundational deep dive. It's into the tech that's arguably reshaping just about every industry out there. The Internet of Things, IoT.
It really is. And, connecting physical devices to the digital world, that brings in a ton of complexity. So, yeah, for this dive, we're aiming to provide a pretty comprehensive toolkit.
Okay.
We'll unpack the essential 5-layer architecture, sort of the gears making these systems work, then the specific, quite demanding skills you actually need to build them.
Right.
And then we'll jump into two really critical high-stakes areas.
Yeah.
Healthcare, that's IoMT, and industrial manufacturing, IIoT.
So the idea is, by the end, you, the listener, should have a really solid grasp, not just what IoT is, but how it's built, why things go wrong sometimes, and where it's all headed.
Exactly. A rock-solid understanding.
Okay, so our sources define IoT pretty elegantly, actually. It's basically connecting physical things.
Yeah.
Could be anything, right? A tiny sensor, a massive factory machine, connecting them to the internet, collecting data, exchanging it. Fundamentally, it's about turning that raw physical information
into actionable digital insights.
Yeah.
That's the core idea.
And to do that reliably, you obviously need a standardized architecture, something robust.
Absolutely. Understanding this layered stack, it's non-negotiable if you're getting into this field. I mean, it impacts everything: power use, security risks, you name it. So let's trace that data journey, starting right where the physical meets the digital.
Okay, so we start at layer 1, closest to the real world. It's called the perception layer.
Yeah, think of it as the system's like sensory nerves. It's the data capture point.
Made up of sensors and actuators.
Exactly. Sensors are the data collectors. They measure something physical, could be temperature like with a thermistor, or something more complex like an accelerometer checking machine vibrations, or a medical sensor measuring blood sugar levels continuously. These devices collecting the data, those are the edge devices.
Got it. And the actuators, what's their role in this layer?
They're the other side of the coin. They complete the loop. They get a command, often from the cloud, way down the line, and they do something physical.
So they act on the information.
Precisely. They're the system's hands or voice or whatever. Could be triggering an alarm sound, shutting off a motor, opening a valve.
Or even something precise like dispensing medication.
Yeah, absolutely.
Right.
Dispensing a specific dose. It's that physical action component.
The classic example in the source material is the smart thermostat. That illustrates this loop pretty well, doesn't it?
It really does. You've got the sensor checking the room temp that's your input.
Right.
If that temp drifts from what you're set, an actuator, the heating or cooling unit turns on or off. That's the output. Simple closed loop.
But, okay, here's where it gets tricky. If you scale that up, say, hundreds of sensors in a factory, you're suddenly generating just massive amounts of data every second.
Oh, yeah. Fire hose of data.
You can't possibly send every single one of those raw readings over the internet, can you? It just wouldn't work.
You absolutely cannot. That's the critical point, and it leads us straight to layer 2. Edge devices and gateways, and this key concept of edge processing.
Edge processing. Okay, so the edge device, that's like a small computer near the sensors.
Exactly. Usually a microcontroller or some kind of embedded computer, physically close to where the data originates. Its main job. Aggregate that data and do some initial processing right there.
Okay, let's unpack processing at the edge. What does that really mean? Are we talking complex AI or?
Not usually, no. Not heavy-duty AI, but definitely crucial processing. Think basic filtering, maybe averaging readings, calculating simple deviation. So instead of blasting out 100 raw temperature readings every second, maybe the edge device just calculates the average over that second and sends that. Or even better, it only sends an alert if the temperature jumps significantly, say more than 2 degrees. It's about being efficient with bandwidth.
Right, saving data transmission.
But it's more than just efficiency. Edge computing enables critical local decision-making.
Okay, why is that so vital? I mean, if we've got these powerful cloud platforms waiting, why not just send it all up there and let the cloud decide?
2 words: latency and reliability. Especially in high-stakes situations. Think about that factory again. If a vibration sensor picks up that trestle, a crucial turbine bearing is about to fail.
You need to act fast.
Instantly. The edge device has to trigger the shutdown immediately. You can't wait, 5 seconds for the data to go to a server hundreds of miles away, get processed by some complex model, and then have the command sent back.
That 5 seconds could be disastrous.
Exactly. Millions in damage or even injuries. Edge computing gives you that near-instant response. And crucially, the system can still act even if the main internet connection goes down temporarily.
Okay, that makes a lot of sense. So if the edge device handles that immediate processing and local action, what's the specific job of the IoT gateway then? Is it just passing data along?
It's more than just a pass-through. Think of the gateway as the secure bridge, the communications hub for a group of devices. It has maybe 3 main roles.
Okay, what are they?
First, protocol translation. You often have edge devices speaking different, maybe proprietary local languages. The gateway translates those into internet-friendly protocols like MQTT or HTTP.
Got it. Makes everything speak the same language for the outside world.
Precisely. Second is connectivity. It provides the actual physical link outwards, could be Wi-Fi, could be cellular, Ethernet maybe.
The on-ramp to the wider network.
Exactly. And third, super important, local security.
Okay. How does the gateway bolster security? Seems like the edge devices are the vulnerable point.
They are, and that's why the gateway is key. It acts like a local firewall. Imagine dozens of tiny, low-power sensors, each trying to manage its own internet connection and security. That's a huge attack surface.
Nightmare scenario.
Right. So instead, those little devices only talk locally, maybe via Bluetooth or Zigbee, to the gateway. The gateway itself is a more robust device capable of handling stronger security measures, things like inspecting data packets, maintaining lists of allowed devices, managing security certificates. It's like a hardened checkpoint protecting the more vulnerable devices behind it.
Okay, so data is processed locally, aggregated, secured by the gateway. Now it needs to actually travel. That takes us to layer 3, the network backbone, connectivity. And you mentioned it's not one size fits all here.
Not at all. The network needs are wildly different depending on the device. A heart monitor someone wears at home has totally different needs than, say, a tracker on a shipping container crossing the ocean. So for short-range stuff, inside a building or a small area, you're looking at the usual suspects. Bluetooth, especially Bluetooth Low Energy, BLE, for power saving. Zigbee is popular for mesh networks, like in smart homes where devices relay messages for each other. And, of course, standard Wi-Fi and wired Ethernet.
Okay, standard local stuff. What about when things are spread out, miles apart?
Then you need wide area networks, WANs. High-speed cellular 4G and increasingly 5G is crucial for applications needing good bandwidth and low latency, maybe video streaming from a remote camera or controlling mobile robots.
But not everything needs that kind of speed, right?
Exactly. And that's where the real game changer for a lot of simple IoT comes in, LPWAN, low-power wide area networks.
LPWAN, like LoRaWAN and NB-IoT.
Those are the big ones, yeah. LoRaWAN, NB-IoT, their defining feature. They sacrifice high bandwidth, high speed for incredible range, sometimes miles, and ridiculously low power consumption.
So the battery lasts forever.
Practically. A sensor using LoRaWAN might send a tiny packet of data, just a few bytes a couple of times a day, cover several miles doing it, and run on a single coin cell battery for 5, maybe 10 years.
Wow. Perfect for things like utility meters or farm sensors.
Exactly that. Smart agriculture, asset tracking where you just need occasional location updates, remote infrastructure monitoring, small data, long distances, long battery life. That's the LP1 sweet spot.
Okay, so we've got the physical connection sorted, but the devices still need a way to talk efficiently over that connection, right? To the gateway, to the cloud. The sources highlight 2 specialized protocols here, MQTT and CoAP.
Yeah, these are crucial. They were designed from the ground up for the constraints of IoT devices, limited power, limited bandwidth, maybe unreliable connections.
Let's start with MQTT, message queuing, telemetry transport. What makes it so suitable?
It's incredibly lightweight, and it uses a publish-subscribe model, often called PubSub. Yeah. The key insight is decoupling. A sensor the publisher doesn't need to know who's listening to its data. It just sends its reading, say, temperature 22°C, to a central message broker.
Okay.
Then any other system interested in that data, maybe the cloud platform, a local dashboard app, maybe an actuator, simply subscribes to the temperature topic on that broker.
So the sender and receiver don't need direct connections.
Exactly. The broker handles routing the messages. This model has minimal overhead, very small message headers, efficient connections. It uses very little bandwidth and battery power, making it ideal for those constrained devices.
Got it. Lightweight, efficient, decoupled. And the other one, CoA, Constrained Application Protocol. How does that fit in?
CoA was kind of like HTTP, the protocol that powers the web but stripped down and optimized for tiny devices.
So simpler than HTTP.
Much simpler. HTTP can have large headers, needs reliable TCP connections, lots of back and forth. CoPIC uses very concise, small messages, and often runs over UDP, which is less overhead than TCP. It's really designed for simple request-response interactions where maybe the full pub-sub model of MQTT is overkill.
So MQTT for ongoing streams, CoAP for simple requests.
Generally, yeah. Though you still absolutely use standard HTTP and HTTPS for things like connecting your final web application to the cloud APIs. But for the device-to-cloud or device-to-gateway communication, MQTT and CoAP are often the workhorses.
Okay. Data captured, filtered at the edge, secured by the gateway, transmitted efficiently using something like MQTT or LoRaWAN. It finally arrives at layer 4, the brain, the cloud and data processing layer.
Right. This is where the big picture emerges. The cloud platform is the destination for all that aggregated data, potentially from thousands or millions of devices.
And its role is everything the edge can't do.
Pretty much. Think massive scale, practically unlimited storage for historical data, heavy-duty processing power for complex analytics, running sophisticated machine learning models to find patterns the edge devices would miss, analyzing trends across the entire fleet.
You drew a distinction earlier between edge action and cloud insight. Can you expand on that?
Sure. Let's go back to that factory machine. The edge device detects the vibration is spiking right now and shuts the machine down. That's immediate action.
Got it.
The cloud, though, collects that vibration data, maybe alongside temperature, energy use, and maintenance logs, from 1,000 similar machines across different factories over 6 months.
Okay.
Then a machine learning model in the cloud identifies a subtle pattern. Machines made in a specific batch operating in high humidity tend to fail after 8,000 hours. That's insight. That leads to changing maintenance schedules or even supplier choices.
So the cloud does the deep, long-term, fleet-wide analysis.
Exactly. That kind of heavy lifting, finding those complex correlations, requires the scale and power you only get from the big cloud providers, AWS, Azure, Google Cloud, and their specific IoT services. It's how you move from fixing one machine to improving the whole system.
And eventually, that insight, or maybe just the current status, needs to get to a person, which brings us to the top layer.
Layer 5, applications and user interface. This is everything the end user sees and interacts with. Dashboard showing factory output, control panels on a technician's tablet, a patient's smartphone app displaying glucose readings, maybe alerts popping up.
And these apps talk to the cloud, not the sensors directly.
Correct. They communicate with the cloud platform, usually via APIs, to fetch the processed data, visualize it, show alerts, and crucially, they also allow authorized users to send commands back down the stack.
Right, like adjusting the thermostat setting on your phone.
Exactly. That command goes phone, cloud, gateway, edge, device actuator. That entire flow, sensor to cloud to app, and potentially back again, that defines the complete functioning IoT system.
Okay, we've dissected the system's anatomy. Now, the big question for anyone listening who wants to build this stuff, what skills do you actually need? The sources really stress this isn't just software. It's a true mix of hardware and software know-how.
Oh, absolutely. It's fundamentally multidisciplinary. You can't just be, say, a web developer who's never touched a circuit board.
Yeah.
You need to understand the physical constraints. The absolute foundation is embedded programming and electronics.
Embedded programming. So coding directly on those little microcontroller chips?
Precisely. You have to be comfortable working with serious limitations, tiny amounts of RAM, maybe just kilobytes, very slow processors compared to a laptop. You need to manage memory carefully.
What languages are key here? Is it all low-level stuff?
Traditionally, yes. C and C++ are dominant because they give you that fine-grained control over memory and performance, absolutely critical when resources are scarce.
C and C++ entity. Steep learning curve for some.
It can be. But interestingly, for slightly more powerful microcontrollers or for faster prototyping, we're seeing a lot more MicroPython, a version of Python adapted for microcontrollers, or sometimes Lua.
So there's a choice depending on the hardware and the goal.
Yeah. Need absolute maximum speed and efficiency, bare metal control, probably CC++. Need to iterate quickly, leverage Python libraries, and the chip has a bit more breathing room, like an ESP32. MicroPython is a great option. But beyond the language, you must have basic electronics knowledge.
Like how to actually connect a sensor.
Exactly. Understanding communication interfaces like I2C or SPI, reading datasheets, basic circuit design principles, power requirements. You need to make sure your hardware actually works and doesn't, let the magic smoke out.
Right, crucial. Okay, so you've got the code running on the chip and needs to communicate. That means networking and communication protocols are next.
If embedded is the brain, Networking is the nervous system. You have to be fluent in that whole alphabet soup of wireless standards we talked about.
Wi-Fi, Bluetooth, LoRaWAN.
Yep. How to configure them, understand their range and power trade-offs, and critically, how to actually use the messaging protocols like MQTT reliably.
What does reliably mean in the context of MQTT?
It means understanding things like quality of service levels, QoS. MQTT has different levels to guarantee message delivery. QoS 0 is fire and forget, may be okay for non-critical data. QoS 1 guarantees at least once delivery. QoS 2 guarantees exactly once. Choosing the right level is vital for critical data. You can't afford to lose a medical alert, right?
Absolutely not. So understanding those protocol nuances is key.
If your data can't get off the device reliably, the whole system falls apart.
Okay, data's flowing out. But we mentioned the sheer volume. That leads to needing data processing and analytics skills.
Right, and this skill spans the entire system from edge to cloud. At the edge, you need to write efficient code to filter out noise, maybe compress data, to minimize what you send. Saves bandwidth, saves battery, saves cloud costs.
And then in the cloud.
In the cloud, you need to handle that potentially massive stream, using tools maybe like Apache Kafka for message queuing or specialized cloud services designed for IoT data ingestion. And the goal isn't just storing it, it's analyzing it. Moving towards, ideally, predictive insights, maybe using lightweight machine learning models even at the edge, or more complex ones in the cloud, to spot anomalies or predict failures.
Which ties directly into the need for cloud computing and web development skills.
Mandatory. You have to be comfortable using the specific IoT services from the big cloud players, AWS IoT Core, Azure IoT Hub, Google Cloud IoT Platform. They handle the really hard parts of managing potentially millions of devices, securely provisioning, authentication, message routing at scale.
So knowing the specific cloud vendor tools is important.
Very. And beyond those core IoT services, you'll likely use other cloud components. Serverless functions like AWS Lambda or Azure Functions are huge in IoT for processing incoming messages without managing servers. And you need web development skills, especially API development, to build the dashboards and mobile apps that actually display the data and allow control.
Okay, that's a lot of ground to cover. Embedded, networking, data, cloud, and the sources emphasize one more critical area, security fundamentals.
Non-negotiable. And honestly, often the weakest link in early IoT projects. We're connecting the physical world here. The consequences of a breach could be severe.
More than just data loss.
Way more. Physical damage, safety risks.
So developers must have a solid grasp of security principles. Think encryption using TLS, transport layer security, the successor to SSL, is fundamental for protecting data as it travels over the internet.
Securing the pipe.
Exactly. Then there's device authentication. How do you ensure only legitimate devices connect to your cloud? Using things like X.509 certificates, secure key storage, unique device IDs. You need strong verification. And what about updates? Devices might be out in the field for years.
That's a huge challenge. Secure firmware updates are critical. You need a mechanism to patch vulnerabilities remotely, over the air, OTA. But that update process itself must be secure and authenticated. You can't risk pushing malicious code to thousands of devices. Security needs to be baked in from day one, not bolted on later.
Okay. That's a daunting but essential skill set. For listeners thinking, okay, I want to start learning this, what hardware should they actually pick up first? The sources recommend 3 key platforms.
Right, for getting your hands dirty. The absolute classic entry point, especially if you're new to electronics and coding, is the Arduino Uno.
Why the Uno specifically?
It's cheap, it's robust. The programming environment, the Arduino IDE, uses a simplified version of C, C++ Weed, and the community support is just unparalleled. Tons of tutorials, libraries, examples.
What kind of project is it good for? Learning the basics.
Exactly. Perfect for learning how to read different kinds of sensors, control simple things like LEDs or small motors, understand basic circuits, maybe build that simple heart rate monitor that just blinks an LED faster or slower. You focus on the core interaction with hardware without worrying immediately about Wi-Fi or complex networking.
Got it. So foundational hardware interaction, what's the next step up? Maybe if you need more processing power or want to run a real operating system.
Then you look at the Raspberry Pi, the Pi 4, or even the smaller Pi 0W. These aren't microcontrollers. They're tiny, single-boarded computers running Linux.
So much more powerful.
Way more powerful. This opens the door to using standard Python, running web servers, connecting cameras, doing image processing, even running lighter-weight AI models directly on the device using frameworks designed for the edge.
What's a good Pi use case in IoT?
Think about a smart camera project. Maybe using a Pi with a camera to monitor an assembly line, and using a simple computer vision script in Python to detect if a product is missing or defective. That kind of task needs the processing power and OS flexibility the Pi provides, which would be impossible on an Arduino.
Okay. Arduino for basics, Pi for more power, and Linux. What about bridging that gap, especially adding connectivity easily?
That's where the third recommendation shines. The ESP32 family, or its slightly older sibling, the ESP8266. These are absolute game changers in the hobbyist and prototyping world.
What makes them special?
They are low-cost microcontrollers, quite powerful in their own right, but crucially they have built-in Wi-Fi and Bluetooth right on the chip.
No need for extra modules or shields.
Exactly. That massively simplifies projects where you need internet connectivity. It's often the natural next step after mastering sensors on an Arduino. Okay, now how do I get this temperature reading onto the internet? The ESP32 is usually the answer.
And using an ESP32 forces you to tackle networking sooner.
It does. You're immediately dealing with connecting to Wi-Fi, sending data, using HTTP or MQTT. And because they're often battery-powered, you start learning critical power management techniques, like putting the chip into deep sleep mode to conserve energy, waking it up only periodically to send data. That's fundamental for real-world deployed IoT.
Okay, device is built, code is running, it's sending data. Where does that data go, especially when you're just starting out? The sources mention Blink for prototyping.
Blink is fantastic for getting quick results. It's a platform designed to make it super easy to create mobile dashboards for your IoT projects.
Drag and drop interface?
Pretty much. Use their app, drag on widgets like gauges, charts, buttons. Then you add a simple Blink library to your ESP32 code, and suddenly your temperature reading shows up on your phone. Or you can press a button on your phone to turn an LED on or off on your device.
So it handles the cloud and app side for you.
It abstracts away a lot of the complexity of setting up servers, databases, and app development, letting you focus on the device logic and seeing results fast. Great for validating ideas.
But presumably for a real product, a commercial deployment, you need something more robust.
Absolutely. Once you move beyond prototyping or small personal projects, you graduate to the big leagues. The major cloud IoT platforms. We're talking AWS IoT Core, Azure IoT Hub, Google Cloud IoT.
And what they offer that Blink doesn't?
Scalability, security, and integration. These platforms are built to handle potentially millions of devices connecting simultaneously. They provide robust mechanisms for securely provisioning devices, managing certificates, handling massive message throughput reliably, and integrating that data seamlessly with the rest of the cloud provider's ecosystem, their databases, their machine learning services, their analytics tools.
So if you're building that smart factory network with thousands of sensors.
They're using Azure IoT Hub or AWS IoT Core. They provide the industrial strength foundation, the security guarantees, and the hooks into advanced analytics that you need for a serious, scalable solution.
Right. We've got the building blocks. Now let's zoom in on where this tech makes a huge impact, starting with healthcare. The Internet of Medical Things, IoMT. You said earlier, if IoT is about uptime, IoMT is about life-critical data. The stakes feel incredibly high here.
They absolutely are. The unique challenges in IoMT really start with data security and privacy. This isn't just sensor data. It's protected health information, PHI.
Like patient records, vital signs.
Exactly. And that immediately brings in heavy regulations. In the US, you have IABA. In Europe, GDPR. These aren't suggestions. They're strict legal requirements with massive penalties for violations.
So what does that mean for someone actually building an IoMT device or system?
It means security and privacy can't be afterthoughts. They have to be baked in from the absolute beginning. Privacy by design. Every piece of data, from the sensor reading a heart rate to it being stored in the cloud, needs end-to-end encryption. Secure transmission using TLS is just the start. You need secure data storage, strict access controls who can see what data, when, and why.
And these devices are targets, presumably.
Huge targets. Think ransomware locking up hospital systems, or breaches stealing sensitive patient data. So device authentication has to be rock solid. You need ways to absolutely ensure that only the correct, verified medical device is sending data for a specific patient, and that no unauthorized person or system can access it or tamper with it.
Okay, privacy and security paramount. What's the next big hurdle specific to medical devices?
Formal regulatory compliance for the device itself. This is a major differentiator from, say, a consumer fitness watch.
You mean getting FDA approval, things like that?
Exactly. If your device is intended to diagnose, treat, monitor, or prevent a disease, like a continuous glucose monitor, an insulin pump, even software that analyzes medical images. It's likely considered a medical device. And adding internet connectivity throws a huge wrench into the already complex regulatory approval process. You have to prove not only that the core medical function is safe and effective, but that the connectivity doesn't introduce new risks. Can the device be hacked? Could a faulty software update cause harm? Does network latency affect its critical function? Proving all this adds significant time, cost, and rigorous testing to the development cycle.
And speaking of latency, the network itself needs to be incredibly reliable, right? Especially if it's monitoring something critical.
Absolutely. Network reliability and latency are life and death concerns here. If you have a remote patient monitoring system designed to send an alert if a patient's heart goes into a dangerous rhythm,
that alert has to get through instantly.
No excuses. Right. A network outage, even a few minutes of delay, could be catastrophic. So IoMT systems must be designed with redundancy in mind.
Like what? Backup connections?
Yes. Maybe the device primarily uses the patient's home Wi-Fi, but it has a backup cellular modem like LTE that kicks in automatically if the Wi-Fi fails. Or the device needs robust offline capability. It has to securely store critical data locally if the network is down, and then transmit it reliably once connectivity is restored. You have to assume failure will happen and plan for it.
And one more practical challenge, especially for things people wear or have implanted: power management.
Huge. Think about a wearable ECG patch monitoring for atrial fibrillation for weeks or months, or a smart pill bottle that needs to track usage reliably. You can't ask patients to recharge these things every day.
So batteries need to last a long, long time.
Months, sometimes years. This demands extreme focus on ultra-low power design, using the most power-efficient components like Bluetooth Low Energy, BLE, instead of classic Bluetooth or Wi-Fi, aggressively using those deep sleep modes on the microcontroller, waking up only for the briefest possible moment to take a reading and transmit. Every microamp counts.
Okay, those are significant hurdles, but the potential payoff is enormous. Let's look at the use cases. Remote patient monitoring, RPM, seems like a huge one.
It's arguably the most impactful application right now. RPM fundamentally changes how chronic conditions are managed, instead of relying on occasional clinic visits or patient self-reporting.
Which can be inaccurate or infrequent.
Exactly. RPM uses connected sensors, could be wearables like smartwatches, patches, blood pressure cuffs, glucose monitors, to collect vital signs continuously or frequently in the patient's own home.
What's the real benefit of that continuous stream?
Early detection and proactive intervention. Take diabetes management. A continuous glucose monitor, CGM, logs blood sugar levels every few minutes.
Okay.
If those readings start trending dangerously high or low, the IoMT platform can automatically flag it and send an alert directly to the patient's doctor or a monitoring service. The clinician can then intervene, call the patient, adjust medication before a crisis happens, before an emergency room visit is needed.
So it shifts care from reactive to proactive.
Precisely. It keeps people healthier at home, reduces hospitalizations, and gives clinicians much richer data to work with. It's transforming chronic care.
We're also seeing IoT built directly into more complex medical equipment, right? Smart medical devices and wearables.
Yes. Beyond simple monitoring, we see connectivity enhancing therapy delivery and diagnostics. Think smart insulin pumps that automatically adjust delivery based on CGM readings, or connected inhalers that track usage. Did the patient take their dose correctly at the right time? This improves adherence.
And diagnostic wearables.
Things like those cardiac monitor patches we mentioned. They can passively record heart rhythm for weeks. Onboard algorithms, sometimes even AI, analyze the ECG data. If something like atrial fibrillation is detected, it can automatically capture the event and notify a cardiologist, often via a secure smartphone app, within minutes. Getting that kind of diagnostic insight outside the hospital walls is revolutionary.
And outside of clinical settings in areas like elder care, IoT provides crucial emergency response capabilities.
Very important application. Fall detection is a prime example. Dedicated pendants or wearables use accelerometers and gyroscopes to sense the specific motion pattern of a hard fall, followed by a lack of movement.
Distinguishing it from just dropping the device.
Right. If a fall is confirmed, the device can automatically initiate a call to emergency services, often providing GPS location data as well. It's a potential lifesaver for seniors living alone.
And it goes beyond just falls.
Yes, smart home sensors can play a role in passive monitoring, tracking patterns of daily living. When are doors opened? When is there activity in the kitchen? How long was the TV on? Algorithms can learn a person's baseline routine. If there's a significant deviation, say, No movement detected all morning when the person is usually active. It can trigger a notification to a family member or caregiver to check in. It provides peace of mind.
Finally, within the hospital itself, IoMT helps with logistics, asset tracking.
This might sound mundane, but it's a huge efficiency booster. Hospitals are complex, sprawling places. Nurses and technicians can waste enormous amounts of time searching for critical mobile equipment. IV pumps, wheelchairs, portable ECG machines, ventilators.
Time they don't have in an emergency.
Exactly. By attaching small, inexpensive tags, maybe Bluetooth Low Energy, BLE beacons, or RFID tags to this equipment, an IoT system can provide a real-time map showing the location of every tagged item. Staff can instantly find the nearest available ventilator or infusion pump. It improves response times dramatically.
And it's used for sensitive items, too.
Yes, particularly for things like managing the cold chain for temperature-sensitive medications or vaccines. Sensors in refrigerators and freezers constantly monitor the temperature. If it drifts outside the safe range, alerts are sent immediately, preventing spoilage and ensuring patient safety.
Okay, shifting gears from healthcare to the factory floor. Industrial IoT, or IIoT, sometimes called Industry 4.0. Here, the focus shifts from patient safety to, well, keeping multi-million-dollar production lines running smoothly. The challenges seem different, but just as intense.
They are. The absolute top priority in IoT is real-time reliability. Downtime is the enemy. In many manufacturing sectors, an hour of lost production can cost hundreds of thousands, even millions of dollars.
So systems have to react instantly.
Instantly and reliably. This is why edge computing is so dominant in IoT. You simply cannot rely on cloud round-trip times for critical machine control or safety interlocks. The decision and action have to happen locally, in milliseconds.
And this drives specific network choices, too.
Definitely. You see heavy investment in specialized industrial networks. Things like industrial Ethernet standards like Profinet or Ethernet that offer deterministic performance. And increasingly, factories are deploying their own private 5G networks.
Private 5G, just for the factory.
Yes. It gives them guaranteed bandwidth, ultra-low latency, and the ability to connect thousands of sensors and machines wirelessly within the campus, which is crucial for flexible manufacturing and controlling things like autonomous mobile robots reliably.
Okay, reliability is key. But here's a huge challenge mentioned in the sources: legacy system integration. Factories aren't built new every year. They're full of old machines.
This is often the biggest headache for IoT implementers. You walk into a factory and you've got machines that are 10, 20, even 30 years old, controlled by programmable logic controllers, PLCs, from that era.
PLCs that were never designed to talk to the internet.
Not even close. They often communicate using older, proprietary industrial protocols that are completely alien to modern IT systems.
Can you name some of those protocols? What makes them tricky?
The big ones you'll encounter are Modbus, which is ancient but still widely used. It's simple but lacks security features. And then OPC, especially the older OPC-DA, data access, and the more modern OPC-UA, unified architecture. OPC-UA is better. It's platform independent, more secure, but still requires specialized knowledge and software gateways to bridge the gap between the OT, operational technology network on the factory floor, and the IT information technology network.
So getting data out of these old systems is a custom job.
Often, yes. It might involve retrofitting new sensors onto the old machine, like adding vibration sensors to an old motor. Or it involves using special industrial gateways that can speak those old protocols, like Modbus TCP or Serial, and translate the data into something modern, like MQTT or an API call that the IoT platform can understand. It requires a blend of OT and IT skills.
And once you get that data flowing, the volume must be immense.
It's truly industrial big data. Think high-frequency sensor readings, vibration, temperature, pressure, acoustics sampled thousands of times per second from hundreds or thousands of points on a complex machine or production line.
How do you even handle that flood?
You absolutely need effective data volume and management strategies. Filtering and aggregation at the edge are critical. You don't send every single raw vibration sample to the cloud. You might calculate RMS values or frequency spectrums, or run edge analytics to detect anomalies first. Data compression is also key. And then, in the cloud or on edge servers, you need sophisticated analytics platforms capable of sifting through that massive volume to find the meaningful patterns, the subtle precursors to failure.
Security in IoT also has a different flavor, doesn't it? It's not just about data privacy, it's about physical risk.
Exactly. Security and safety are intertwined. Historically, many industrial control networks were air-gapped, physically disconnected from the internet for safety.
But IoT connects them.
Right. And that opens the door to new risks. An attacker could steal valuable intellectual property, like manufacturing processes for formulas. Or, much worse, they could potentially manipulate machinery remotely, causing equipment damage, production halts, or even creating serious physical safety hazards for workers on the floor.
So IoT security needs to be incredibly robust.
It has to be. This involves things like strict network segmentation, keeping the critical machine control network isolated from the business network and the internet, continuous monitoring for unusual activity, strong authentication for any device or user accessing the system, and importantly, designing systems to fail safe. If connectivity is lost or the system is compromised, the machinery must default to a safe, non-operational state.
One last challenge before we hit the use cases: the upfront investment, initial costs, and ROI.
Yeah, IoT isn't cheap to implement initially.
Yeah.
Sensors, network upgrades, software platforms, integration services, it requires significant capital expenditure. So projects need a clear, demonstrable return on investment, usually focused on reducing downtime, improving quality, or increasing efficiency. And there's a human challenge, too.
Training staff.
Training existing factory staff, who might be experts in mechanics but not IT, to work with these new systems. And also addressing potential employee fears about automation leading to job losses. Change management is a big part of successful IoT deployment.
Okay, despite the challenges, the value proposition is clearly there. Let's talk use cases. The number one most cited benefit seems to be predictive maintenance.
It absolutely is. This is the killer app for IoT because it directly tackles that massive cost of unplanned downtime. It's a fundamental shift in maintenance strategy.
From reactive to proactive.
Exactly. Instead of fixing machines after they break, reactive maintenance, which is expensive and disruptive, or replacing parts on a fixed schedule regardless of their actual condition, preventive maintenance, which can be wasteful.
Predictive maintenance uses data to forecast failure.
Right. By continuously monitoring key parameters, vibration, temperature, oil analysis, acoustic signatures using dedicated IoT sensors, you can detect the very subtle signs of a specific component, like a bearing or a gear, is starting to wear out long before it actually fails.
How does it make the prediction? Is it AI?
Often, yes. Machine learning models, sometimes running right at the edge, are trained on historical data in real-time sensor readings. They learn the normal operating signature of a healthy machine and can detect deviations that indicate impending failure.
So the system flags a potential problem early.
Exactly.
Yeah.
It generates an alert, maybe days or weeks before the failure would occur, telling the maintenance team, bearing 3 on pump 7 shows signs of wear, recommend replacement during the next scheduled maintenance window. This allows them to schedule the repair proactively, order parts, and avoid that costly, unexpected shutdown. The ROI is usually very clear and very fast.
Beyond just maintenance, IoT enables smarter process automation and robotics, right?
Definitely. Connected machines and robots on a production line can coordinate their actions much more effectively. They can adjust speeds, sequences, or parameters in real time based on sensor feedback from upstream or downstream processes, or based on commands from a central manufacturing execution system, MES. This leads to smoother production flow and higher throughput.
And quality control gets a boost too, using sensors instead of just eyeballs.
A massive boost. Traditional quality control often relied on manual inspection or sampling. IIoT enables 100% inspection in real time using sensors and, increasingly, AI-powered vision systems.
AI vision, like cameras watching the products.
Exactly. High-speed cameras connected to edge computing devices analyze every single item coming off the line. They can check for dimensional accuracy, surface defects, correct labeling, fill levels in bottles, seal integrity on packages, things a human inspector might miss, especially at high speed.
Can you give a concrete example of that in action?
Sure. Think of that bottling line again. An IoT vision system checks the fill level of every bottle. If it detects one that's underfilled, running on an edge device,
it reacts instantly.
Instantly. The edge system signals a downstream robotic arm or an air jet actuator to push that specific defective bottle off the conveyor belt into a reject bin. It logs the defect, maybe even correlates it with upstream filler performance.
Yeah.
All happens in milliseconds, ensuring only perfect products proceed, drastically reducing waste and customer complaints.
Very cool. Finally, there's a big push for sustainability and cost savings through energy management and smart facilities.
Yeah, this often provides surprisingly large returns. Factories are huge energy consumers. IoT allows for granular monitoring of energy usage, electricity, gas, water, right down to individual machines or production cells.
So you know exactly where the energy is going.
Precisely. Smart meters, current sensors, flow meters feed data into the IIoT platform. This data, maybe combined with production schedules or occupancy sensors in different building zones, allows the system to automatically optimize energy use.
How? Like turning things off?
Yes, but intelligently. Dimming or turning off lights in unoccupied areas. Optimizing HVAC settings based on real-time conditions and occupancy. Even adjusting machine parameters slightly during peak energy price periods, if production allows. It all adds up to significant cost savings and a smaller environmental footprint.
Okay, we've grounded ourselves in the current reality of IoMT and IIoT, the challenges and the big use cases, but this field moves fast. What's coming next? The sources point to three major trends shaping the future. First, this idea of distributed intelligence.
Yeah, this is a really fundamental shift. We're moving beyond just collecting data centrally and then analyzing it. The intelligence itself is spreading out. The big drivers here are edge computing and fog computing.
We talked about edge computing for latency. What's the broader trend here? What's fog?
Edge computing is processing right on the device, or a very nearby gateway. Fog computing is similar, but maybe involves a slightly more powerful layer of computing infrastructure closer to the edge than the central cloud, perhaps a local server within the factory or hospital. The core idea for both is pushing processing away from the centralized cloud and closer to where the data is generated.
Why the big push? Resilience and cost.
Those are huge factors. Processing locally means critical functions can continue even if the main internet link goes down. That's resilience. And it drastically reduces the amount of raw data you need to constantly stream back to the cloud, which saves enormous bandwidth and cloud processing costs. Developers are now seriously focused on deploying sophisticated logic, even AI, directly onto these edge devices.
So AI integration, AIoT, isn't just a cloud thing anymore. It's moving to the edge.
Absolutely. That's maybe the most exciting part of distributed intelligence. We're seeing the rise of tiny ML machine learning models specifically designed to run on resource-constrained microcontrollers.
Tiny ML, like AI on an Arduino class device.
Potentially, yes, or more likely on slightly more powerful chips like the ESP32 or specialized AI accelerators for the edge. This means the device itself can do more than just collect data. It can understand it in real time.
Give me an example.
Okay, think about an industrial acoustic sensor listening to a machine instead of streaming the raw audio constantly to the cloud for analysis.
Which would be a ton of data.
Right. A tiny ML model running on the sensor itself could listen for the specific sound frequency pattern that indicates a bearing is about to fail. The device only sends an alert if it detects that pattern. It's making an intelligent decision locally. It transforms the device from a dumb sensor into a smart, autonomous agent. It's about acting on insight, not just collecting data.
Okay, smarter devices at the edge. The second big trend is in connectivity evolution. 5G gets a lot of hype. What's its real impact on IoT?
5G brings a combination of three things that previous cellular couldn't quite deliver together for IoT at scale. 1, massive device density, connecting potentially millions of devices per square kilometer. 2, high bandwidth when needed. But 3, and perhaps most critically for many future applications, ultra-low latency.
How low are we talking?
Down into the single-digit milliseconds range for communication. That kind of responsiveness unlocks applications that were previously impossible or impractical over wireless.
Such as?
Things like remote surgery, where a surgeon uses robotic arms controlled over the network you need near-instant haptic feedback. Or large-scale autonomous systems like vehicle-to-everything, V2X, communication.
Cars talking to each other.
Cars talking to each other, to traffic lights, to pedestrians' phones, sharing hazard information or coordinating movements instantly to improve safety and traffic flow. That requires the massive connection density and low latency of 5G.
And beyond 5G, what about connecting things in really remote places?
That's where the other connectivity trends come in. We continue to see growth in those LPWAN technologies like LoRaWAN and NB-IoT for applications needing years of battery life and long range over raw speed. But the really interesting new frontier is satellite IoT.
Using satellites for IoT, like satellite phones.
Sort of, but optimized for small data packets from IoT devices. New constellations of low Earth orbit, LU satellites, are coming online, offering relatively low-cost connectivity literally anywhere on the globe.
So places with no cell service at all.
Exactly. Think tracking ships or containers across oceans, monitoring environmental sensors in remote wilderness areas, managing agricultural assets in vast rural regions, tracking pipelines or equipment in deserts. Satellite IoT promises to finally provide truly global coverage for low-bandwidth applications.
Okay, smarter devices, better connections everywhere. The third trend focuses on system integrity, digital twins, and enhanced security. What's a digital twin?
A digital twin is essentially a dynamic, virtual representation of a physical asset, system, or process. Imagine a perfect, real-time software model of a specific jet engine or an entire factory floor, or even a model of a patient's cardiovascular system.
And it mirrors the real thing.
Precisely. It's fed constantly with real-time data from the IoT sensors on the physical counterpart. So the digital twin reflects the current state, condition, and performance of the real thing.
What's the point of having this virtual mirror?
It allows you to do things that are impossible, expensive, or dangerous to do on the physical asset. You can run simulations. What happens if I increase the speed of this machine? How will this change in production layout affect workflow? You can test software updates on the twin before deploying to the real system. You can use it to predict future failures with much higher accuracy by running accelerated simulations. You can even use it to train AI models or human operators in a safe virtual environment.
So it's a sandbox for optimization and prediction.
A very powerful one. It's becoming crucial for managing complex industrial assets and systems.
And finally, security continues to evolve. We're moving towards zero trust.
That's the paradigm shift. The old model of trust but verify, or assuming anything inside the network perimeter is safe, that's gone. Zero trust means never trust, always verify. Every device, every user, every connection attempt has to be authenticated and authorized every time, regardless of where it's coming from.
How is that being implemented in IoT?
We're seeing a move towards hardware-based security, using secure elements, dedicated tamper-resistant chips on the IoT device to store cryptographic keys and device identities securely. This makes it much harder to clone or spoof devices. We're also seeing stronger authentication standards and a bigger push for security by design, building security considerations into the entire product lifecycle from the very beginning, not trying to patch it on later. The goal is inherent trustworthiness, verified continuously.
Wow, okay, that was a comprehensive journey. We've gone from the fundamental 5 layers of IoT architecture, dug into the specific tough challenges in healthcare and manufacturing, and looked ahead at these really transformative trends like edge AI, ubiquitous connectivity, and digital twins.
That's a lot to take in for sure. If you're listening and thinking, okay, I want to actually start building something, my single biggest piece of practical advice is don't try to boil the ocean.
Meaning?
Don't try to learn everything embedded, C++, WAR, Python, MQTT, LoRaWAN, AWS, Azure, machine learning all at once. You'll get overwhelmed. Pick one piece of approachable hardware. I personally think the ESP32 is a fantastic starting point because it has that built-in Wi-Fi and Bluetooth.
Okay, one board.
And pick one relatively simple cloud platform or dashboard service to send data to, maybe Blink like we mentioned or something like ThingSpeak. Focus on mastering that single end-to-end flow, getting sensor data from your ESP32, sending it reliably over Wi-Fi using MQTT or HTTP, and seeing it appear on that simple dashboard.
Master the basics first.
Nail that fundamental loop. Once you understand that completely, then start adding complexity. Try different sensors, explore different protocols, move to a more powerful cloud platform, maybe experiment with TinyML, but start simple and focused.
That makes sense. For listeners who prefer a more structured learning path, maybe online courses or books, what do the sources recommend?
There are some excellent resources out there. For a good conceptual overview combined with practical labs, Coursera has a popular Introduction to the Internet of Things and Embedded Systems specialization. Microsoft also offers a really great free 12-week curriculum called IoT for Beginners on GitHub, which is very hands-on and uses Azure.
Then for book learners.
A couple stand out. So, Internet of Things, a hands-on approach by Baga and Matasetti is often recommended. It covers concepts well and includes practical exercises. For understanding the design trade-offs involved, Designing the Internet of Things by Adrian McKeown and Hakeem Kasmali is also excellent.
And beyond formal courses, the community aspect is huge in IoT, right?
Absolutely essential. Don't underestimate the power of forums, like the official Arduino forums, the ESP32 forums on sites like eEspressifs, and of course, Stack Overflow. And for project ideas and step-by-step guides, websites like Hackster.io and Instructables are treasure troves.
So find a project that looks interesting.
Yeah, find something that excites you, maybe building a smart plant watering system, or a connected weather station, or garage door monitor. Following a practical project guide, hitting roadblocks, debugging the hardware, and the code that hands-on struggle is where the real learning happens. And these blended skills truly solidify.
Okay. We started this deep dive talking about how IoT turns raw data into actionable insights. As we wrap up, let's reflect on where these trends are taking us. You talked about the synergy ubiquitous 5G enabling massive numbers of devices, edge AI making those devices smart and autonomous.
Right. Think about that convergence. Historically, most connected systems collected data, maybe displayed it, and then a human looked at it and decided what to do. The action step was often delayed and human-mediated. Now, with powerful AI running directly on devices at the edge, coupled with low-latency networks like 5G, that loop sense, analyze, decide, act can become nearly instantaneous and fully autonomous.
Removing the human from the loop in some cases.
Potentially, for certain tasks. So here's the final thought I want to leave you with. Consider your own daily life, maybe at home, maybe at work. Think about tasks that currently involve human observation, interpretation, and then manual action. Which one of those tasks, monitoring something, adjusting something, responding to something, is now genuinely poised to become completely automated, where the device itself can intelligently perceive its environment, make a sophisticated decision, and act on it immediately, with no human intervention required at all.
Moving beyond just collecting data to instantly acting on it.
Exactly. That shift from passive data collection to autonomous action is the profound change underway. Understanding that transition and having the foundational knowledge we've discussed today equips you not just to understand the future of IoT, but potentially to build it,